Good morning, everybody, and welcome to the class. Today, we shall learn about canal regulation. So, let's begin the lecture. Here in this sketch, you see a schematic diagram of the canal system. Right here is the river, which is our source of water, and from the river, we take out the main canal. From the main canal, we take out the branch canal and then distributary and then minor. Uh, and after the minor, we have water courses. So this is the whole network. And when we take out the water from the river, or we take out a branch canal from the main canal, we have to make sure that the right amount of water that goes to the branching canal. And for that purpose, we need to uh, measure it, or I would say regulate it. So basically, this distribution is proper distribution is called regulation. Let me read it for you. Water that enters into the main canal from the river has to be divided into different branches, as you can see here, and distributaries in accordance with the relative urgency of demand on different channels. And this distribution process is basically called regulation. Okay? To distribute the water effectively, the discharge has to be adjusted and to the desired value. So to adjust that desire to the adjust the discharge to the desired level, we need to regulate the discharge. This aim is achieved by mean of regulator. So the process is called regulation, and the structure which we use for regulation is called a regulator. Okay, canal regulation works. This term works is used for structures which we built on our canal system. So a regulator is basically one of the works, and there are others as well um, that are listed right here. The works which are constructed in order to control and regulate discharges, depth of water, velocities, etc. in the canal are known as canal regulation works. These structures ensure the efficient functioning of canal irrigation system by giving full control upon canal. So the main thing is that we want to control the water according to our desire, and that is not possible without constructing these structures. So some of the important structures we built on our canal system are canal falls, canal regulators, head regulator, cross regulator, canal escapes, metering flume, and canal outlet and modules. Today's lecture will focus mostly on canal regulators, canal escapes, and metering flumes. Canal fall, we shall have a separate lecture, and that will be after the midterm, and canal outlets will also have a separate lecture. Okay, so here in this sketch, you see this main canal, or you can call it a parent canal. So from the parent canal, you see we are off taking a branch canal here. So on the parent canal, right here is a structure which we call cross regulator. So the structure which we built on the parent canal is called cross regulator, and right here is a structure which is on the off-taking canal, that is called head regulator or distributary head regulator. Okay, so on the branch we have head regulator, and on the parent canal we have cross regulator. And here you see another structure which is called escape. We shall study about escape in the later slides. It can be on the off-take canal, it can be on the parent canal, it can be anywhere wherever it is needed. And here you see on the parent canal, we have a drop in the level. This is called canal drop or fall. So wherever there is a significant level difference on the ground, we create these falls, and we shall study the fall later on, as I mentioned before. Okay, canal regulators. Uh, let's talk briefly about the alignment. Here you see that we have a parent canal, and from the parent canal takes off a branch. Okay, this is an off-taking uh, canal. And on the off-taking canal, you see right here we have head regulator, and on the parent canal which continues, we have the cross regulator. And in this arrangement, you see that this is a smooth transition. Okay, the off-taking canal is smoothly transiting out of the parent canal, and the center line here, if you trace it back, right here, the angle of the off-taking canal center line is 0 with respect to the center line of the parent canal. Okay, the ideal arrangement is when off-taking channel or canal is the same thing here, makes 0 angle. Right here, the angle at the beginning is 0 with the parent channel initially, and then separates out in transition. Okay, the transition will have to be properly designed so as to avoid accumulation of silt jetty. Silt jetty means you can say a small collection of silt which may be you can say you may have here. We don't want silt jetty. It's like a small mountain of silt. Uh, we don't want that because it reduces the cross section of the canal and thus affecting its efficiency. So you have to design it properly. Another arrangement is this, where the off-taking canal does not make the center line of the off-taking canal does not make a 0 angle here, but right from the beginning there is an initial angle, okay, which is not 0, and is a similar arrangement of taking canal moves from in one direction, and the remaining parent canal that moves in the other direction, and again cross regulator on the parent canal and the head regulator on the off-taking canal. And you can see that here the uh, width of the parent canal is more, and after some water is taken off, the width of the parent canal that reduces. Another arrangement is here, um, when the parent uh, when the parent channel has to be carried straight. Right here you see this is the parent channel, and it has to be carried straight after the off-taking canal is taken off. So this arrangement is used when the parent channel has to be carried straight. The edge of the canal rather than the edge of the canal rather than the center line should be considered in deciding the angle of the off-taking canal. Okay, uh, the edge of the canal, uh, this edge of the canal, is right here. This is the edge, and right here, this is the edge. So edge changes. Okay, let's talk about distributary head regulators and cross regulator. A distributary head regulator controls the supply of the off-taking channel, while the cross regulator controls the supply of the parent channel. As we discussed before, the cross regulator is on the parent channel, head regulator is on the off-taking channel. The head regulator provides at the head of the off-taking channel, controls the flow of water entering in the new channel. So you have gates in the head regulator as well as in the cross regulator. So if you want to control the supply of water in the new channel, just control it from the gates of the head regulator. While the cross regulator may be required in the main parent channel downstream of the off-taking channel, and it is operated when necessary to head up, this is the important word here, head up water on the upstream side to ensure the required supply in the off-taking channel even during the periods of low flow in the main channel. Now, sometime the water in the parent channel is less. So what you do is you close the gates of the cross regulator. When you close the gate, the water starts heading up in the parent channel. And when enough water has headed up, then you open the gate of the head regulator, and the required amount of water can go to the off-taking channel. So that's the purpose of the cross regulator. Okay, so looking into the head regulator a little bit in more depth, more main functions of head regulator. Again, the head regulator is right here on the off-taking channel. Okay, to regulate or control the supplies entering in the off-taking channel. So you close the gate and you let the water flow in the off-taking channel. To control the silt entry into the off-taking channel. Now, it may be in some situations the parent channel has higher silt if there is some rain in the upper reaches. So the silt uh, quantity is higher, and you don't want the silt to enter in the off-taking channel because the channel off-taking channel is smaller. If excessive amount of silt enters into this, then the cross section may get compromised. So you uh, control it. So you can close the gate when the silt is higher in the parent channel. To serve as a meter for measuring the discharge, of course, when you release the water, you must know what is the quantity of water. You only want to release the desired quantity, and cross-regulate the head regulator also functions as a measuring device for the discharge. Okay, the next is main function of the cross regulator. Again, the cross regulator is on the uh, main or parent channel to effectively control the entire canal irrigation system. Now, because it's on the parent channel, when you operate these gates, you can control the entire downstream of the cross regulator, means the entire network downstream of the cross regulator. When the water level in the main channel is low, this is what we talked before, that it is used for heading up the water. You close the gates, head up the water, and then uh, release in the off-taking channel. They help in absorbing fluctuation in various sections of the canal system and in preventing the possibility of breaches in the tail reaches. In the tail reaches, for example, if there is a breach which has already happened downstream of the cross regulator, or there are chances of breaching, you see that the banks have become weak and the breach can happen. So in both scenarios, you immediately close the gates of the cross regulator, and that will prevent the breach downstream of the cross regulator. Okay, and absorbing fluctuation is similar to what we talked before, that if the water level is low somewhere in the parent channel, you close those gates for water to head. Cross regulator is often combined with the road bridge. So there is a provision of bridge as well, so as to carry the road which may cross the irrigation channel near the site of the cross regulator, because the canal divides the villages and the lands of the people. So you need to provide bridge for people to pass, for the traffic, for even for the animals, cattle, etc. So you also provide the bridge. It is also usually combined with a fall if required at the site of the cross regulator, when it is called a fall regulator. So basically, sometime there is a fall, okay, level difference. So at the location of the cross regulator, you also provide this fall. So now it becomes a fall regulator. Okay, so a bridge, a cross regulator, a fall, they may be combined. Uh, yes, components of the regulator. Here, this is a picture which can describe the components. For example, the first one you see here, these are called piers. Okay, Uh, in old times, we used to make these piers with bricks. Now we use concrete. And these piers come with gates. Right here, you see, a little bit dark at the back. These are either we may have gates or planks. Okay, planks can be used for small channels only, as the maximum height of the plank that be handled manually is about 2 meter. Okay, uh, plank is a flat piece of metal or steel. So it's not like a gate, but it's just that you can raise it or lower it with the help of cables or something. For large channels, either hand operated or mechanically operated gates can be used. So for bigger channels, we use gates. The hand-operated gates can have a span of 6 to 8 meter, while mechanically operated gates can be as wide as 20 meter. Okay, wide means the width between the piers. Okay, and right here above the piers, you see this is the bridge which people can use to cross the canal. And there is a steel bridge here as well, right here. So on this top steel bridge, you have motors, and right here, these planks are connected to the motors with the help of the cables which are suspended here. And when you run the motor, the with the help of these cables, the plank start moving up. So you can decide where to stop. You want to open the gates fully or partially, it's up to you. A light bridge platform, this light bridge platform right here, and you can also see the stairs to reach that platform. A light bridge platform has to be laid on the piers for the operation of the planks or gates. It is often economical to combine a regulator with a bridge and also to flume the channel. Flume means to reduce the width, right? Here you see the channel width is reduced. This is called fluming. And also to flume the channel at the side of the regulator so as to reduce its floor width for affecting current, because structures are expensive. So you want to reduce the width of the channel so that the structure is smaller, and then after the structure, I mean downstream the structure, you again widen the cross section of the canal. So this was briefly about the regulators types and their components. The next type of structure we want to talk about is called canal escape. As the terminology tells you, escape means to flee away. So here, the escape word is used for a structure which is used to remove the surplus water. Sometime in the canal system, you have surplus water, maybe because of excessive rain or because of some mistake the at the regulator. So excessive water comes into the canal system. So you remove that surplus water and put it into some natural drain. Okay. The water in the irrigation channel may become surplus due to some mistake. Difficulty in regulation means sometimes you have electrically operated gates and you open the gates and then there is power failure and you are not able to close the gate, or the gates are jammed, or some accident happened, you are not able to close. Then excessive water will go into the canal system, or due to excessive rainfall. So there can be different reasons, as I said. Sometimes farmer may find that demand of the water is over. Maybe there is rain and the water demand of the farmer is fulfilled by the rain and he doesn't need the water from the canal. So what he does, he closes the outlet. Okay, when he closes the outlet, then there is excessive water in the canal system, which may overflow and it may damage the banks unless it is escaped using the canal escapes. Okay. No doubt in all such circumstances means when water is surplus, the supplies shall be reduced or stopped from the headworks. but the effect of this reduction is felt only after a certain time. Therefore, in order to avoid the damage, some immediate action is required, and this is achieved by means of escape, generally called surplus water escape. Okay, so these escapes, uh, you can consider these escapes as our safety wall in the canal. The minimum capacity of the escape is generally kept half of the channel capacity at the point of escape. Means if the channel is say 200 cubic, uh, you design it the escape for say 100 cubic, half of it. Okay, I asked such things in the quiz, so these are basic facts. So some of the questions in the quiz may relate to basic facts. Okay, there are two types of canal escapes. One is called weir type, in which you construct a weir. You see, this is a weir. And the other is regulator type. Regulator type means there are gates. Right here, you see, there are gates. So you can open and close the gates. That's actually called regulation. So you have regulator type. So in the weir type, what do you have? Look at this cross section. This is this is the bed level of the canal, and you are looking in the longitudinal direction of the canal. Um, okay, this is the bed level, and this is the canal full supply level, and this is the top of the canal bank. Means this is the freeboard, you can say. So look at this weir. This is the cross section of the weir. So the canal full supply level matches the crest level of the weir. Now, if the water level in the canal goes above the full supply level, what will happen? It will automatically start, moving outside the canal. Okay, the water will go outside the canal, fall here, and go to the natural drain. Okay, there are no gates here, nothing. It's just open, and you will see that then the water automatically, nobody has to come and open the gate, nothing. It just goes above the uh, crest of the weir automatically. Okay, crest level of the weir is kept at full supply level and no gates. Now in the regulator type, again you see right here is the bed level of the canal, and this is the full supply level. Now here is the escape channel, and you have gates and piers and gates, of course they are together. So whenever you want to release the water from the canal, you open the gates and the water will go into this channel, and this channel will take away the water and put it in some drain or river. And above this you have a bridge as well. Okay, and platform for gate operation. Crest level of the escape is kept at the bed. This is the crest level of the escape, and it matches the bed level of the canal. So crest level of escape is kept at bed of the canal, and gates are used to regulate. Now, both of them have their own advantage. In this case, there are no gates. It means that nobody has to come and open the gates. But the water will go above the weir only when it is above the full supply level. If it is below full supply level, then this weir will not be effective. Okay, this escape will not be effective. But in this case, the crest level is at the bed level. Yeah, even if the canal is half full, you can still open the gate and the water will escape. So both have their advantages. Okay, uh, let me show you a picture of the weir type escape. Look at this. This is a weir type escape. So this is a canal, longitudinal, and whenever the water, you know, crosses this level, which is the crest level of the weir, it will start overflowing from here, and it will, go away, maybe joining some drain. So you see there are no gates, nothing. It's just everything is open and accessible, and whenever the water crosses that level, it goes right into the drain. Okay, so these are escapes. Then the last thing we want to talk about is metering flume. The word meter comes from the same concept as we have electricity meter and the gas meter. which basically measure what electricity we have consumed, what gas we have consumed, because ultimately we have to pay for it. Same is here. We have metering flumes which are used to measure the discharge, because the quantity of water is always limited, and we only want that the agreed upon or the desired share of water should go to a particular canal. Okay, and it is flumed. Okay, that we have artificially flumed it or narrowed it, because it becomes easier. One thing is that the cost is less, and the other thing is that it's easy to make the measurement on a smaller section. Okay, so a metering flume is an artificially flumed or narrowed section of the channel which can be utilized for calculating the discharge in the channel. Normal section of the canal is narrowed by masonry walls by a splay of 1:1. This is the ratio how you reduce it. I will show you on the next slide. So this is the slope when you narrow it down and make it a rectangular cross section. General cross section of the canal is trapezoidal, but at the meter we make it rectangular. It becomes easier for us. And that rectangular section is called a throat. From where and after the throat, the channel is slowly diverged so as to attain the normal section by means of masonry wings with a splay of 2:1 to 10:1. That depends on the situation, economics, and the situation at that particular site. More gradual convergence and divergence, less will be the loss of head in the flume. Okay, if you abruptly converge it, abruptly diverge it, the head loss will be more. Uh, Gradual convergent divergence, head loss will be less. Let me show you the picture. There are actually two types of meter flumes. One is Venturi flume, and the other one is standing wave flume, which is the next slide. So you see here the width of the canal, the actual width of the canal, B1, and then you gradually converge it on both sides and make a throat, rectangular cross section, and then gradually diverge it to attain the same cross section as before the meter. And right here you see it's a full supply level, and there is some head loss downstream. Of course there will be some head loss, and here you have the stilling wells. From the stilling wells you measure the depth of the water. One is just before the throat and the other one is right in the throat. Okay, so in the stilling well it's like a well, and the water is still there because it is out of the flow, so that helps us in measuring the depth of the water accurately. So Venturi flume, it consists of gradually contracting channel leading to a throat, and gradually expanding channel leading away from it, gradually expanding, leading away from it. Stilling wells are provided for measuring head at the entrance and at the throat. If the H is the difference in the two wells, means you measure the head here, you measure the water level here. Here the water level was say 4.5 meter, and here the water level is say 4.4 meter. So there is a difference of 0.1 meter. So if H is the head difference in the two wells, Q can be calculated using this formula. The head difference H is right here. G is the acceleration due to gravity. C, D is a coefficient which varies from 0.9 to 1. And then A1 and A2, area at the entrance right here. And it appears to me that this B1 is the average width. You multiply the average width with the depth of the water. A2 is the area at the throat. It's a rectangular cross section, so width into the depth of the water right here. Okay, so this formula ultimately gives you the flow at this meter flume. The next one is standing wave flume. Now standing wave is the hydraulic jump. You see here the canal bed, and then you see this crest, downstream glacis, and when the water flows above this, right here the standing wave or the hydraulic jump is formed, and the upstream full supply level and the downstream full supply level, there is a uh, you know some loss of head is there. And in the plan, upstream, convergence, rot, divergence, and then restoring the cross section. So if a hydraulic jump is formed on the downstream glacis right here, it is called a standing wave flume. The length of the throat, this length of the throat is the length of its throat is at least 2 to 3 times the head over the crest. Right here, this H is the head over the crest. For example, the head of the crest is say 2 meter. Then the length of the throat may be 4 to 6 meters. Okay. Um, if H is the head above the crest, Q can be found like this. 1.7 CD is the same coefficient. B is the width of the rod right here, whatever is the width, and H is of course the head above the crest. So you plug in this formula and it will give you the flow. Okay. So again, the main purpose of the metering flume is to measure the flow because we want to accurately distribute the water within the network of the canal system. So that concludes this lecture. Thank you very much.